Namaste and welcome to Apna Gurukul, one step towards success. We are discussing about the number system chapter of class 9th NCERT. We have already dealt with the introduction of the chapter where we dealt a little bit about the definition of rational numbers and what are we going to cover in this particular chapter. So let's begin with what is required for this particular video. Are we clear with the number line? I'm very much sure that we are clear with what is a number line and how do we plot numbers. Now in the coming videos, we will be exploring a lot about our number line as well. Then are we clear about the definition of rational number? We'll revise after quite a while to define irrational numbers. We need a thorough knowledge of rational numbers. And then we will extend our number system in this particular video. So let's begin. Let's go with the quotation. Maths is a series of questions giving meaning to many more such questions. That's pretty interesting, right? If you're whatever you understood from this quotation, you can comment down. We can talk about this a lot. So let's start defining irrational numbers. Now, in this particular video, we will focus mostly on defining irrational numbers, and there'll be two definitions we will be discussing. Number one definition is based on the definition of rational numbers what we gave, and the second definition is about decimal expansion. Let's get into one by one. So numbers on the number line which are not rational, can we say that they are irrational numbers? Because we ended the last video by questioning you that are there some more numbers on the number line, and I said absolutely yes. So can we say that apart from rational numbers, whatever numbers are there on the number line, they are irrational? Can we say that? And I say absolutely yes. So how do we define it? Define the rational numbers, and on the basis of that we will define irrational. So any number which can be represented in the p by q form where q is not equal to 0 and p and q are integers, they are called as rational numbers. We have already referred this. So now, are there any numbers which cannot be represented in the p by q form? That's my $100 questions. Just for joking. That's the $1,000,000 question, that are there numbers which cannot be represented by p by q form? And that is what is the definition, number one definition of irrational numbers. A number S is said to be irrational if it cannot be represented in the form of x by y, where x and y are integers. And I'm sorry, here it should be y. Y is not equal to 0. Y is not equal to 0. So that's what is a definition number one of rational numbers. Irrational number, I'm sorry. But you might be thinking, how do we get to know about irrational numbers? And how does that number look like if it cannot be represented in the p by q form? We will understand that with the number story and then with decimal expansion. How are those numbers represented? And then we will discuss a few more topics related to that. So what happened was Pythagoras, who is known to be the discoverer of irrational number in around 400 BC, he was looking for some shapes. He worked a lot about geometry. So when he was working with right triangles, he found out that if somehow we have the right angle triangle which is isosceles, and their two sides are 1 units and 1 units, he found out that hypotenuse cannot be measured with any instrument, any kind of instrument. We generally measure the length with a ruler, right? Ruler or inch tape. He found out that this particular length, when this is 1 unit and the other side is also 1 unit, the hypotenuse cannot be measured. So when he applied Pythagoras theorem, and he is the discoverer of the Pythagoras theorem, he found out that the length of hypotenuse will be, as you know, the hypotenuse square, c square is equals a square plus b square, right? We already know about this formula. So c square is equals, one of the sides is 1 unit, so 1 square plus the second side is also 1 unit, so 1 square plus 1 square. So c square is equals 1 plus 1, that is 2. So c will be under root 2 units. Now, since this number was cannot be represented on the number line, then mathematicians started to think, and Pythagoras said that this is such a number which cannot be measured by any kind of instrument, because its decimal expansion never end, and it cannot be represented by a p by q form. And that's how we started to get irrational numbers. And after this discovery in around 425 BC, Theodorus of Cyrene, they proved that I'm sorry, it's not root 4. Root 4 is should not be here. Root 5, root 17, all the under root of prime numbers are all irrationals. And after that, after working for so many years, Lambert and Legendary, they found out that even pi is an irrational. Now you might be thinking that we have been representing pi is equals 22 by 7. This is a pi by q form. And p, that is 22, is a integer. 7 is also an integer. But how can we say that pi is an irrational number? So my dear friend, 22 by 7 is an approximate value of pi, which we use for basic calculation. When we start growing up in mathematics, pi, the value of 22 by 7 in place of pi is not used at all. So that is just an approximate value which we have been given to understand the circles and the related shapes better. Okay, so do not misunderstand that since pi can be represented as 22 by 7, it is not an irrational. That's completely wrong. 22 by 7 is just an approximate value. Pi is an irrational, which was proved by Lambert and Legendary. Now, coming on to the definition of real numbers, when we found the rational and irrational numbers all together, so we got a definition that when rational numbers and irrational numbers are brought together, we get a set of numbers which are called as real numbers. They are called as real numbers because after these numbers, there are no possible numbers which can be expressed on the number line. So what does that mean? Is there any more number left on our number line? Absolutely not. Absolutely not. And that is why our number line is also called as real number line. Now, my question to you all is for you all to think. There's already answer is given, but you must think: are there any more numbers left? I'm not talking about are there any more numbers left on the number line. I'm asking, are there any more numbers left? The answer is yes, but we are not focusing on that right now. We'll study about that in class 11. Those are called as complex numbers. And when you go to BSc and you explore mathematics more and more, you will get many more different variety of numbers. Now, moving towards the definition 2, as I told, we will have 2 definitions. So moving towards the definition 2, we must focus on decimal expansion of numbers first. So whenever we have numbers in the form of p by q, and we know that p by q form is known as rational numbers, and they are represented as quotient q. That means we can always divide them and get to a result. Yes or no? Yeah. So we will try to understand how does that work. 17 over 3, it can be represented at 5.666666. So now if you are a little bit confused about how do we go around that, so we will quickly discuss of how do we divide. So the denominator is the divisor and the numerator is the dividend. So 3 5s are 15. We subtract it, so we get a remainder as 2, and then we put a decimal place, we get a 0. 3 times 6 is 18, and as you observe, this 2 as remainder will keep on coming because every time we will multiply it by 6, and 2 as remainder will keep on coming. That means this decimal expansion is never going to end. The 6 is going to repeat again and again and again and again. So that is one of our observation. What's the next observation? Let's focus. Now here we have 2 by 7, 2 over 7. When you divide 2 by 7, as you can see, 2, 8, 5, 7, 1, 4. And then once again it starts to repeat 285714. So instead of repeating it once again, we have a representation called whatever number is repeating, we just put a bar over that. This particular number can be represented as 0.285714 bar, right? So the this is the other criteria, like more than one numbers are repeating together and they will keep on repeating and repeating, they will never end. The decimal expansion never ends. Let's go about 23 by 8. When you divide 23 by 8, we'll go for the division quickly. 8 and 23, so 8 times 2 is 16. Then we get 7 as remainder. We put a decimal place. 78 times 8 is 64. And then we get 6 as the remainder. So 0. So 8 sevens are 56. And then we get as 4 as remainder. 8 fives are 40. And that's how we get to a 0 remainder, and we get 2.875. Over here, the decimal expansion ends. And that is a very, very important conclusion. So with these examples, what do we observe? We will take a look at that. The number one observation is the remainders either become 0 after a certain stage or starts repeating themselves. I repeat, they either become 0 or they start repeating themselves. The second observation is the number of entries in the repeating string of remainders is less than the divisor. What do we observe? As you can see over here, the remainder is 7. So as you can see, after 2 to 4 and plus to 6, after 6 decimal places, it starts to repeat themselves. It cannot repeat after 7 or 8 decimals. If it has to repeat itself, then it must repeat below 7, means before 7 or before 6 decimal places. As you can see in the first case, the divisor is 3 and it started repeating from the first itself. It cannot start repeating after 3. That is very, very important observation. You can take few more examples and try to understand this point. The third point, if the remainders repeat, then we get a repeating block of digits in the quotient. If the remainders are repeating, then in the quotient we get a repeating block of digits. And the fourth and the most important is this is true for all rational numbers, and that is how we have two new terminologies to refer. And on the basis of these two new terminologies, we define first rational numbers and then irrational numbers. So we have something called as recurring and terminating decimals. So the decimal expansions which end after a few places are called as terminating decimal expansions. As you saw in the case of 23 over 8, it ended after 3 places. So this is called as terminating decimal expansion. Now, the decimal expansion which does not end after a few places but keeps on repeating is called as recurring decimals. I hope that makes sense. If it is not ending but repeating, that is called as recurring or repeating decimal expansions. Now, if the decimal expansion is not ending, it does not end, it is called as non-terminating. And if it does not repeat also, it is called as non-recurring. Yes, so that's how we reach to the definition 2 of irrational numbers. Any numbers or the number with decimal expansion as non-recurring and non-terminating. It is not terminating as well as it is not repeating also. They are called as irrational numbers, and that gives us the definition, the second definition for irrational numbers. And let's summarize this particular topic what we were discussing. If we have a decimal expansion, if it is terminating, then it is rational number. We are not worried about that. If it is non-terminating, then there are two conditions. Either it will keep on repeating, so it becomes recurring. If it is recurring, it is a rational number. If it is non-recurring, then it is irrational number. So what do we observe? We observe that non-terminating, non-recurring decimal expansion gives us irrational numbers. I hope that makes sense. Now think about, my friends, is it possible to prove, I repeat, is it possible to prove that 0.2777 means 272727 is a rational number? But how or why am I asking this question? Because we have studied that a rational number must be represented in the form of p by q, where p and q are integers and q is not equal to 0. So can we repeat a non-terminating decimal expansion but recurring decimal expansion, that's a rational number, into p by q? If we can do that, we are very much sure that they are rational numbers. We'll study about that, and yes, it's absolutely possible. We'll study about that in the coming videos, and the proof will be done in higher classes. We'll just show it that how 0.277 or similar numbers which are non-terminating but recurring are rational numbers, and how it can be represented in the p by q form. So keep thinking till we discuss that particular topic. So before we move on to the next video, as always, we have some set of questions. Are all real numbers irrational? I repeat, are all real numbers irrational? The answer is no, my dear friends, because 2 is a real number, it's a rational number, but it's not an irrational number. Now, your question will be, are all irrational numbers real? Absolutely, because real numbers are made up of rational numbers plus irrational numbers. I hope you remember that definition. Now, are all irrational numbers rational? That's absolutely not, because there is a clear distinction that they both are opposite to each other, I would rather say, because a rational number can be represented in p by q form, where p and q are integers, where q is not equal to 0. But irrational numbers definition is completely the opposite, a number which cannot be represented in the p by q form, where p and q are integers, right? So all the irrational numbers can never be irrationals. Now your question might be, are all natural numbers irrational? Absolutely not. 2 is a rational number, I have already given. 2 is a natural number, but it's not an irrational. Are all natural numbers rational? That is also not true, because, oh, sorry. Are all natural numbers, I thought the other way around. Are all natural numbers rational? Absolutely yes. Why? Because whatever natural number you write, you can always give it a denominator 1, and this becomes p by q form, and that is why they are all rational. Next question. Are all natural numbers real numbers? Absolutely yes, because all natural numbers are rational, and all rational numbers are real numbers. So obviously, all the natural numbers are real numbers. Now, final question. Are all integers real number? Absolutely yes, because all the integers are rational number, which we have seen in the previous video itself. So since all the rational numbers are real numbers, therefore all the integers are also real numbers. I hope this question clarifies everything about these kind of number system. Now we will start exploring all these number systems to have lots of operations with them, and the most important, how do we represent that on number line, coming soon in the coming videos. Thank you so much for being here with us and learning something new. Apna Gurukul, one step towards success. We'll see you in the next video. Until then, keep smiling. Jai Hind.